All right. So here we have a CSTR, which if you remember from my one of my earliest videos, um, is continuously stirred tank reactor. And this time we're actually putting a reaction through it. So it's not just going to be volumetric flow or anything. It's going to be slightly more complicated. So to start, we have our initial conditions, Q0, CA0, and T0, and we have a cooling jacket pumping water at some cooling temperature. I will determine that for the coding later. Um, and Q, and this is the overflow reactor. So my last video, I think I confused these two parts. But this is the overflow reactor where Q in is equal to Q out, which is just equal to a Q. So anytime you see Q, it's going to be the same for both. T is equal to the temperature out, so I'll just use temperature for that. And I don't think we're going to use this, but there is a hotter temperature of the cooling water. We want to try and find E, Ca, dt, and or the change in concentration and the change in temperature. We need both of those. To start, we need to define things. So Q is equal to the overall heat transfer times area times the temperature minus the temperature of the cooling water, the temperature of the reactor minus the temperature of the cooling water. Because we do have to take that into consideration because I believe this is an exothermic reaction. We'll determine that later in the coding, so if I'm wrong here. But for now, we're treating it like some sort of exothermic reaction. And I mean, this would be over a K term because you don't want just temperature in the final, because I believe this is joules per minute or some unit of time. This is this U term here is the overall heat transfer coefficient. So that is in like joules per minute meter squared. All these units do eventually go into joules term. But so we get that Q there because Q is more than just the volumetric flow at this point. It's also the temperature. And so we want to say this K term here, K is equal to K0 e to the activation energy over the gas coefficient and temperature. I believe we want this term to be negative because it's the activation energy. So that's what that K term is right there. We do have a reaction going, so we need to define the reaction rate. Ra is equal to KCA. That's pretty simple, straightforward. And then here, we need not forget that there is also a volume term for both of these, and that will be divided out later, because we do actually have a set volume since it's an overflow tank reactor, which I think for later it'll be 100 liters, but that's not important now. We're just working with variables. So this is equal to CA in, CA minus CA in, and then minus KCA, because we have that reaction term, A is disappearing. This would actually be, we need KCAV, so just divide everything by B. You get that term out of there, so it's just Q over V. And we're good with that. See, pretty simple for that, straightforward. Now T, on the other hand, this is actually got some terms in front of it. We need the density, the heat capacity, and I think we already have volume. So we need the terms Q, rho, C. We need Q times the density times the heat capacity times the temperature in minus the temperature. And actually, I think I mixed these up, so it's just CA and CA in. Yeah. This is a very wet marker. CA in minus CA. And we need the overall heat transfer, T minus TC. And we actually, since this is an exothermic reaction, we need to factor in the heat of, or the enthalpy of reaction. And that is going to be times this KCAB term here. Divide everything by rho CPV, and we get, and I'm just going to rewrite it so it's simpler. dt over dt equals q over v, t in minus t minus ua over rho CPV T temperature minus the cooling temperature minus the heat of reaction. This might be plus, not minus, because if we had it as plus, and it was endothermic, we would want to factor that in. So then we've got enthalpy of reaction, KCA over rho. All right, and there are our differential equations. These two, and we can put those into coding now.
So we have this problem here where we need to find the time-dependent material and energy balance of the constantly stirred tank reactor and blah 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 code. We're on the coding portion now because I've already derived all the equations. And I already wrote all these down on a separate piece of paper so I don't have to keep coming back here. So I'm just going to go ahead and fill these all out. So our flow is equal to 100 liters per minute. Our concentration in is equal to 1 mole per liter. Our starting temperature into the tank is equal to 350 Kelvin. Our volume is equal to 100 liters. Our density is equal to 1,000 grams per liter. We've got our, I believe, heat capacity is, no, come on, there we go. Our heat capacity is equal to 0.239 joules per gram Kelvin. Our negative enthalpy is equal to 5 times 10 to the 4th joules per mole. Our ER, E over R, and I'm just going to rewrite it as ER, is equal to 8,750 Kelvin. Our initial K is equal to 7.2 times 10 to the 10 over 1 over minutes. Our heat transfer coefficient is equal to 5 times 10 to the 4th. Our cooling water is at 300 Kelvin. Our initial concentration, or our concentration coming in through the pipeline, is equal to 0.5 moles per liter. Our initial temperature, I guess I already have initial temperature. Time is going to be equal to 10 minutes. Alright, so there's all that data to be front loaded. And we got to define a function for the tank, and that's going to be with respect to time and a vector quantity. And that vector quantity will be equal to concentration and time. Nope, concentration and temperature. What am I doing? And then we need, saving failed. Why ever so? Do I not have internet? Alright, I got all the technical difficulties dealt with. Okay, back to where we were. So now we need to define a k, and k is going to be equal to that k naught e to the e activation energy, blah blah blah, that. I'll write it out. So k naught equals numpy, it's numpy.exp k0 times the e. It's the initial k value er over t, and I believe it has to be negative. Okay, there's that equation, and then we need our time-dependent material. So dCA, because we did CA first, or dCA dt. Our change in concentration with respect to time is going to be equal to Q in over V. It's just Q. Yeah, Q over V. Q over V times CA in minus CA, and then it's minus K times CA. Alright, and then our dt is going to be equal to Q over V times temperature, change in temperature, minus the heat transfer coefficient over rho V, and then heat concentration, density, volume, heat capacity, and then multiply that by by T minus TC minus, or actually this will be plus delta HR times K times concentration over density and heat capacity. And we need to return that in an array of dCA and dt. Alright, now we gotta solve IVP this, so result is equal to solve IVP. And then we need to have this as our tank, and with respect, and from 0 to t, method is Rado, whatever you pronounce it, and then our dense output needs to be true. Oh wait, I need YO is going to be an array. I need this to be the array of initial concentration and time, or temperature. Didn't I define T0? Ah, I put it as T in. That makes sense. I'm getting this confused with the last one that I did. Yeah, I did CA0, okay. Alright. And then we want to plot this. So we need to make a time plot, numpy linspace. We want it from 0 to t with 500 intervals. On our concentration plot, is the result with respect to t plot. Make a plot of this. And rows equal to 1 and columns equal to 2. Okay, and then we need to have this be CA plot, This needs to be C plot. This needs to be T plot. And then we go ahead and name it. And that should work. Oh. Alright, there we go. Let's see. I don't know if that's right, but we got something. Alright, I believe this is right, so now we get to play with this, with what happens when your cooling water changes temperature, so 301. Yep, and then you get a very big spike in temperature and a very big drop in concentration, because as temperature goes up, the reaction speeds up and therefore uses all the concentration, and it goes down to 0. And it eventually goes to steady state, so it does normalize, so it's not awful, but this could make a tank explode. And it happens if we go to 302, so even just like little 1 centigrade changes have a drastic, okay, that's about the same. I was actually expecting these to be a little bit different. Yep, there we go, there's another one. And if you take the time to go out here, let's say 30 minutes, you'll see it keeps oscillating, and it's just going to keep doing that. But if you, let's go back to 10 minutes for the scope of the problem. If you even take it up to 305, it oscillates even faster, and it oscillates within that 10-minute period that you can see with an initial spike. And if I was to take this up to 310, let's see what happens. It just spikes, flat lines, and has a little bit of dying oscillation. There's another one of these, I don't remember what temperature, that should like have these oscillations, but it goes, I'm pointing at the screen, you should, I hope you guys have been able to see this whole time, but I just realized this camera's been knocked to the side. But there should be one that starts dying with oscillation. It might be like 308. Yeah, okay, it does. It's around there. But if I set this to 290, it works as expected. The concentration rises and the temperature falls. So the cooling water does work. Even with just 20 degrees of temperature difference can mean a whole lot of variation in this. And also another thing that we can do is see what happens when you make it exothermic or endothermic. So you make this number negative, and that's pretty straightforward. And now it just behaves normally. And then you want to raise the cooling water temperature so you can actually add heat. So let's say 50. The reaction rate rises probably a little more, and even less concentration appears. 400. And with 400, you get barely any change in concentration, barely any change in temperature, because it's the reaction's going much faster. So, yeah, let's reset that, everything. The textbook calls this a steady state reaction, but it is not steady state to begin with. It has a rise in concentration and a rise and a fall in temperature. So even at 300, the cooling water works, but it does not already pre-done as a steady state. And that should be it for this video and homework series.